Can, Doctor.
Okay, thank you, Samuel. Alright. So let's proceed on today's lesson. Well, today we're going to continue on the classification of fluid flow as well as Bernoulli equation. So I would like to recap what we have learned on the last class. We learned on how to derive the velocity and the acceleration vector in the form of Eulerian description. Alright. Remember that Eulerian description focus on space and time, while the Lagrangian refer to the time only. So based on the velocity, we have velocity vector in terms of magnitude. We have x, y, z and time. Okay, x, y, z is a space, t is a time. As well as the acceleration. Okay, we have the local acceleration as well as convective part, which is represent the space. And then we did one example regarding to 2D velocity field by the given equation here. All right. And this is your homework. So now let's proceed on the classification of fluid flow. So how to classify the fluid flow? So in 3D flow, the velocity vector depends on three spatial coordinates, which is x, y, and z. At the stagnation point, a point at which the fluid decelerates and comes to the rest. Alright. So, for example, this is the fluid particle and then move here to the bottom, to the downward and then immediately stop. That is why the velocity of the particle equal to 0. This is what we call a stagnation point. Okay, Timothy, do you have any question? Okay, I cannot hear you, Timothy. Alright, when the flow involve one-dimensional, that means the velocity vector depends on one variable. That means u is depends on the radial. Different in radial direction will have different velocity. So another one is we call as a developed flow. So what is developed flow? Developed flow in which the velocity profile. So what is velocity profile? This is velocity profile. This we call a velocity profile. Okay. Velocity profile doesn't vary with respect to space coordinate in the direction of flow. Alright. For example, you have the flow. The velocity profile is still the same. Okay, the velocity profile unchanged in the direction of flow. So this is what we call a developed flow. However, for the uniform flow, is one in which the fluid property are constant over the area. For example, this is the uniform flow. It is uniform throughout the flow. It is the same velocity. Whatever the radial it is the same. Okay. So, next we move on to the inviscid flow and viscous flow. So, for example, viscous effect, okay, for the viscid flow, viscous effect doesn't significantly influence the flow. However, for the viscous effect, okay, effect of viscosity are important. Okay, how to locate whether it is viscous or inviscid flow? For example, this is the aerofoil. Okay, we have the aerofoil. This is aerofoil, cross-sectional view. So, surrounding the aerofoil, close to the aerofoil, we have the boundary layer. The boundary layer is basically near the surface of aerofoil. Inside the boundary layer, it is involved viscous flow. Okay, viscous flow inside the boundary layer. For the inviscid flow, it is out of the boundary layer. So basically in the boundary layer, you can see clearly the flow of the velocity. For example, this is the surface. The velocity will be like this. This is velocity profile. Okay, it will be long like this. So this is velocity profile. Okay. And then for the viscous flow, that means inside the boundary layer, it is either laminar or turbulent. So what is laminar or turbulent? So I want to show you clearly. We have we have a group of people walking towards the same direction. Okay, towards from left to the right. Okay, traveling in a flow direction orderly. So this is orderly manner. So that means same velocity and same direction. So this is what we call as a lamina, very smooth flow. And the motion of the flow is very small, okay, slow. Okay, Hairi, do you have any question?
Okay, Doktor.
Huh?
Doktor share screen ke tak?
I share the screen.
Oh
Are
ya.
you able to see the screen?
Cannot, Doktor.
Saya juga tak boleh nampak.
Doctor.
Others, can you see the screen?
Yes, doctor. Can see.
Yes, doktor.
Okay. Okay, can you try to log out and log in again?
Just now I
Saya
have
rasa
tried but
balik.
cannot.
Okay, let me use another internet connection. Wait, yeah. Okay, class, can you see my screen again?
No.
Can you see my screen again?
Can, Doctor.
Okay, good. So, after you have learned about the viscous, inside the viscous, we have the lamina and turbulent flow. So how to differentiate whether it is laminar or turbulent? You can see the orderly manner. Alright, for orderly manner, that means it is laminar flow. For the turbulent flow, it is chaotic manner. Alright, it is flow in different speed and direction. For example, you can look at the pipe flow with disruption. You can see if you put one sensor here, velocity sensor, okay, velocity sensor, it is of course turbulent and it will appear like this. Okay, the velocity over time, the flow of the water velocity at that position will be like this. Alright, so sometimes scientists or researchers have a difficulty to calculate the unsteady flow. So what they do, they normalize, they average the flow. We call it to become the time average physical quantity. Okay, so they use the Rans method. Rans refer to the Renault average Navier-Stokes turbulent model. So they average this, it will become like this. Okay, even it is turbulent, but we can do the calculation after we do the average of the flow. So normally, how to this one we can differentiate of the flow by looking at it. How to differentiate when we have a different kind of situation? Okay, so in order to differentiate the different kind of flow, we understand that if the Renault number, okay, it is basically refer to the Renault number. Alright, the Renault number is the indicator whether the flow is laminar or turbulent. So if the Renault number for the rough wall pipe around 2000, okay, when the flow more than 2000, it is considered turbulent. Alright, for the parallel plate, if the flow Renault number is is more than 1500, it is considered turbulent. Same goes to the flat plate. So when we look at the flat plate, this is the flat plate, right? Definitely the flow from here to here is Renault number less than 3 multiplied with 10 the power of 5. Okay, within the laminar to turbulent, we have transition. Okay, after the transition, go up. Okay, we have the Renault number more than 3 the power of 10. 3 multiplied with 10 the power of 5. Okay, so that means the flow here, I show you, very smooth. Okay, however, in here, it become transition. In here, it become chaotic flow. Okay, it become flow like this. Okay, it's very difficult to predict. So let's take a look example 3. 2 cm diameter pipe is used to transport water at 20 degrees Celsius. What is the maximum average velocity that may exist in the pipe for which laminar flow is guaranteed? So we look at here, the rough wall pipe can be used as the calculation when the Renault critical is 2000. So to make sure the flow is laminar, we must make sure the Renault number critical. Okay, here we use the Renault number critical 2000. Okay, and then the formula of Reynolds number is velocity diameter over nu. This nu refer to kinematic viscosity. And this is the velocity and this is pipe diameter. To make sure the laminar flow is guaranteed, we must make sure it is within 2000, right? And then you can see what is the maximum average velocity. So of course, we must equate the Reynolds number equal to 2000 to get the maximum velocity. Alright, because having the maximum velocity, the flow will change slightly to become turbulent. So we need to know what is the maximum velocity. So here, right? Here we can equate Reynolds number equal to velocity diameter over nu. So in order to get velocity, which is Reynolds number nu kinematic viscosity over diameter. So Reynolds number is 2000. Okay, kinematic viscosity is 1 multiplied with 10 the power of -6. This one from table. Okay, at temperature 20 degrees Celsius. This is for water, yeah. Okay. And then divide with diameter, which is 0.02 meter. So end up you will get 1 meter per second. You can see it very slow. So the velocity here is 0.1 meter per second to make sure it is laminar flow. When the velocity more than 0.1, that means it is turbulent for sure. Wait, yeah. Okay, class, can you hear me?
Can, Doctor.
Okay, sorry, internet. So my internet very poor. Alright. Okay. Now what do you see, class? Do you see the Bernoulli equation?
Yes, yes.
Yes.
Okay, good. So next we go to the Bernoulli equation. Bernoulli equation relates to the pressure, velocity and elevation. Valid in the region of steady, incompressible flow where the friction is negligible, and normally it is outside the boundary layer and wicks. So where is the boundary layer? For example, we have the aerofoil, okay, and then we have the flow. So, and then we have the boundary layer. Right, this is the boundary layer where the viscous effect is very important. So, at the end of this tip, we have the wick. Okay, the rotations of flow. So, this wick is not eligible for Bernoulli equation. No for Bernoulli equation. But this region, okay, this region, very smooth region, it is good for Bernoulli equation. Okay, for example, this region is okay, okay, no problem for Bernoulli equation to apply. Okay, there is a limitation lah. Bernoulli equation only apply for the smooth flow outside the boundary layer. So here, first I want to derive the acceleration of the particle because I'm going to use in the Newton law. Okay. Hairi and Nail, are you able to see my screen? Do you have any problem?
No, doctor, can see.
Okay. So, first I need to derive. Yes.
There's some people on the group asking if you can repeat question 3. Because
Pardon?
it was, there's some people on the group asking if you can repeat question 3 because it was laggy.
Example 3. Okay. Okay, thank you. So, in the example 3, okay, the 2 centimeter diameter pipe used to transport the water at 20 degree. What is the maximum average velocity may exist in the pipe for which laminar flow is guaranteed? Alright, remember here, in order to cause it to become turbulent, okay, it must achieve the highest or sufficient velocity in order to convert to become turbulent flow. So this lamina initially it is very slow. For example, this particle slow, increasing the speed until this maximum speed. So this still considered as lamina. When it increase further speed, it will become turbulent flow. So the question asks to find this speed, okay, the maximum speed before it become turbulent, V max. So this V max supposedly, okay, relates to the V max directly relates to the critical Renault number. So when we use the critical Renault number, this is V max. So Renault number equal to V max, this is critical, V max D over nu. So we rearrange a velocity. Okay, we rearrange velocity equal to Renault number critical. Nu is a kinematic viscosity over diameter. So Renault number critical is 2000. Renault number critical, where I get? From here. Okay, this is rough wall pipe. So just substitute, and then the kinematic viscosity is following the table. At water 20 degrees Celsius, you will get 1 multiplied with 10 to the power of -6. And then divide with diameter 0.02, you will get 0.1 meter per second. Okay, is it clear? Okay, is it clear, class?
Yes, doctor.
Yes.
Okay, good. So Bernoulli equation on the other hand, as I mentioned, this is the rule lah. Bernoulli equation relies heavily on the pressure, velocity and elevation, Z. So why we start with the acceleration of fluid particle? Because I want to use the summation of force equal to ma. So I need to derive A first, okay, in terms of fluid particle. So the motion of particle, the path it follow describe the velocity vector as a function of time and space. Alright. So let's say we have the fluid particle moving in the streamline direction. Okay, maybe the fluid particle here. This is the fluid particle from here, move here. Okay, let's say it is moving at ds. Okay. And then we separate here, this is acceleration following the streamline direction. And then we have the acceleration following to the normal. Alright. So, AS basically is the acceleration, is a streamline. Acceleration. Okay. This follow stream line path. However, for the AN is a normal acceleration. Okay. In direction. Okay, normal to the streamline. Okay. Path. So basically AN, okay, AN is equal to V squared over R, where R is radius of curvature. Okay, curvature radius. AS is due, maybe in order to cause AS is due to change in speed along streamline. AN is due to change in position. Okay. So here we know that dV is equal to partial derivative of S, partial derivative of V over partial derivative of S multiplied with ds plus partial derivative of V over partial derivative of t dt. This is how we want to show you in terms of time and space. Alright. Thus, the acceleration, okay, acceleration dv over dt equal to equal to partial derivative of v over partial derivative of s ds over dt plus partial derivative of v plus partial derivative of t dt over dt. This is one to show you in terms of time, and this one in terms of space. Okay, so this one we can cancel out. All right, so we're gonna have, okay, and then this also we can cancel out when we consider a steady flow. Steady flow, that means there is no change of property. Okay, no change of property over time. The property means the velocity lah, but there is a change of the distance. Okay, so d can put this way, partial derivative this one time equal to 0. So now our final equation for AS is dv over dt equal to partial derivative of v, partial derivative of s, ds, dt. So this one is a v, basically velocity. So it become partial derivative of v, partial derivative of s. Okay. Also it will be the same dv. Okay, this is v, ds. Alright. So now we can see that AS is equivalent to V dV over ds. Alright. Let's start with the derivation of Bernoulli equation. We have the flow. Okay, from this one lah. Okay, basically this is a path line. We can put this way. Okay, this is the streamline over the aerofoil. So maybe it goes from here, initially at here. We can say this is the distance. So this is ds, distance, and it follow the path. This is as, and then this is an. It is same thing like this. Alright, now let's start with the Bernoulli equation. We have the x and z direction, and then the particle move from here to here. Okay, so we can have the distance of the particle. Maybe this is a ds. Okay, this is the path. Alright, and then this is let's say this is element. Okay, we consider this as element. Of course, it has the wick. Okay, downwards. Okay, and then this is the normal. This is the theta. Okay, and this must have the force. We have the force. So the force is pressure multiplied with area, dA. The area of this here, here. Here, in order to get this force, this force is P plus the change of pressure, dA. Okay, because this pressure, this point of pressure, you must plus at this point of pressure, the change of pressure, dA. And this is the weight. Now apply the Newton's second law. Summation of force in the streamline direction equal to mass multiplied with acceleration in streamline. Alright. So from here, I want to show you from this one, I put this triangle. Okay. So this is the change of S. Remember, this is S. And then this is the change in X. And this is a change of Z. This theta refer to this theta. Okay, wait ya, class. Okay. So from here, alright. Alright. So we want to show you the triangle. Alright. So now start with the summation of force in the streamline direction equal to MA. So the force acting to the right is positive. Okay, left negative. So we start with PDA. PDA is positive minus bracket P plus DP. Okay, DA. And then minus W sine theta. Because this week, you must separate it in this direction and then this direction. So of course, it is sine theta to get it this way. Equal to mv dv ds. Where do I get v dv ds from here? Okay. So the reason I introduce you with the triangle because I want to replace with sine theta. So sine theta opposite over hypotenuse. So opposite is okay dz, hypotenuse is ds. So I want to replace here dz over ds. So before I replace, I want to expand further. So PDA minus PDA minus dPDA minus W, okay, dz over ds equal to mv dv over ds. Alright, this one we can cancel out because the same term. So what we have now, it is negative dp dA minus W dz ds equal to mv dv ds. Alright. So this W and mass, I want to replace in terms of volume. So how to get the mass? Okay, how to get the mass? Okay, let's say this is how to get the weight. Weight equal to mass multiplied with gravity, right? So here, mass is equal to, right? Mass is equal to rho multiplied with volume. Thus, the volume of this element is ds. The change in this one multiply with the area dA. So now it become m equal to rho ds dA. Okay, so I can get here W equal to rho G ds dA. I plan to substitute in this W and the mass. So after I substitute negative, I put it here. Negative dP dA minus W, which is rho G ds dA bracket dz ds equal to mass is a rho ds dA dV ds. So I want to cancel out ds with ds, ds with ds, dA with dA and dA. So what I got now is negative dP minus rho G dz equal to rho dV. And I rearranged back the equation. dP plus, okay, dP, this one I rearrange and divide with rho. Okay, remember I left with the velocity here. Supposedly we have the V, right? So this must have B. Rho V, yes, right? So this over density plus V dV plus rho, sorry, plus G dz equal to 0. Alright, so after we have come up with this equation, we can do the integration both sides. Okay, after we do the integration of both sides, because we want to have the complete solution. This is only small finite element. Okay, small element of fluid. We want to do maybe a very large group of fluid. So we need to integrate. So I integrate this one, it become P over rho plus V squared over 2 plus GZ. Okay, plus constant equal to 0. This constant move to the other side. Come P over rho plus V squared over 2 plus GZ equal to constant. So that means this constant, maybe we have the flow, this point and this point, constant 1 should be constant 2, equal. Alright, so C1 shall be equal to C2. So this is, maybe this is C1, this is 1, 1, 1. Okay, so when it is involved 2 point, okay, at 2 point, we can use P1 over rho plus V1 squared over 2 plus GZ1 equal to P2 over rho plus V2 squared over 2 plus GZ2. This is the Bernoulli equation involving 2 points. So from here, we can see this is the flow energy. So what is flow energy? The energy require the fluid to flow. Okay, that means it is because of the pressure. So you put the pressure to the fluid, it will cause it flow. For example, this is a shrink. Okay, this is shrink. This is needle. Alright. You push it with pressure, so this fluid particle will flow. So this is what we call a flow energy. You need the pressure. That is why it is a pressure over rho. And this part, on the other hand, is a kinematic energy, and this part is the potential energy. Alright. So basically, the Bernoulli equation involves flow energy, kinetic energy, and potential energy. Alright, let's take a look at the example 4. The wind reached a speed of 144 km per hour in a storm. Calculate the force acting on the window facing the storm. The window is in the high-rise building. So the wind speed is not reduced due to the ground effect. That means it is out of the boundary layer. Okay, so it is suitable to use the Bernoulli equation. Okay, let's say this is the earth lah. Okay, this is building. This is window. Okay, near the we have the wind flow. Okay, surrounding of this is a boundary layer. Because inside here, we have the viscous effect. So that means this viscous effect, okay, is within the boundary layer. So our case is out of boundary layer. It is suitable to apply the Bernoulli equation. So now I want to convert. This is not SI unit. Okay, the velocity given here is kilometer per hour. So convert meter per second. So everyone, please give me answer. What's the value if you convert from kilometer per hour to meter per second? What is the value? Class?
40.
40 meter per second. Perfect. So to convert it, V equal to 144 kilometer per hour multiply with 1000. Sorry. Okay, this is 1 kilometer equal this one multiply with 1 hour 3600 second. Okay, you will get 40 meter per second. Okay, because you cancel this one, cancel this one, cancel this one, cancel this one. Alright. So you know that the velocity is 40 meter per second. So the question asks, what is the force? Okay, what is the force acting at the window? Okay, the force. So we must know the pressure lah, because the pressure force equal to pressure multiply with the area of the window. So we must know the pressure here. Pressure at 2. So pressure at 1 as well. Okay. So the velocity at 2 and velocity at 1 is given. What do you think the velocity at point 2? At point of window?
0.
Yes. Velocity at the window is 0 because it is at the stagnation point. For example, we have the flow from here and suddenly hit the window. So it is decelerating and stop at the window. So the velocity is 0. 0 velocity. Alright. What do you think of the elevation? The elevation H, maybe the Z. The Z1. Z1 and Z2. Is it the same? Yes, it is the same. Z1 equal to Z2. So now we can apply directly Bernoulli equation, which is V1 squared over 2G plus P1 over gamma plus Z1 equal to V2 squared over 2G plus P2 over gamma plus Z2. Okay, you notice that there is a difference. The previous one we derived in different way. Okay, you can see this is different. Why I use a different formula? Basically, it is the same thing. Why? Because from this one, pressure over rho plus V squared over 2 plus GZ. I want to divide with gravity. So pressure over rho G is basically gamma lah, plus V squared over 2G plus Z. Now can you see it is the same thing? Okay, V1 squared over 2G. Okay, so we can cancel out Z1 and Z2. Velocity 2 is equal to 0. So now what we have, we need to find pressure at point 2. So rearrange the equation, you will get P2 equal to rho V 1 squared over 2. So the rho is the rho of air, yeah? Rho of air is given or not? Okay, it is given 1.27. So 1.27 multiplied with velocity that we have converted before, which is 40. Okay, 40 squared over 2. Now, the final answer is 1016 Pascal. This is pressure. Remember the question asked the force acting on the window. So, based on our equation of force equal to pressure at 2 multiplied with the area of the window. So pressure is 1016 Pascal multiplied with the area of the window, which is 0.9, 1.8. So 0.9 multiplied 1.8 is equal to 1646 Newton. Alright, or simply to make it clear, 1.646 kilonewton. Okay, so far any question?
No, Doc.
Okay, thank you.
Doctor, I have a question.
Okay, yes.
Can you explain why Z2 is equal to Z1?
Z2 equal to Z1.
Yes.
Okay. Just imagine this is the Earth. And this is the high-rise building because of this. Right. So we take this point. This is Z1 and this is Z2. Okay, clear?
Yeah.
So it is the same. Okay?
Oh, okay. Okay, I got it.
Alright. Since we can see that we have deal with the stagnation point where the fluid particle when reaching the obstacle, it will decelerate and stop immediately. The velocity will become 0 while the pressure will increase drastically. Why? Okay. This is the reason. For example, we have the ball. Alright, and then we have the flow. So we have a flow. And then this is the particle of moving particle. Upon reaching this one, the velocity will decelerate, right? So what happened when the velocity decelerate and become 0? What do you think happened? Please try your imagination. Please imagine what happened when the particle hitting the ball. What happened?
Pressure maximum.
Okay, pressure maximum, why?
Because
Why it become maximum? The keyword maximum. Why it is not feel the pressure only? Why the pressure suddenly become maximum?
the kinetic change to the other energy.
Okay. you can see when it reach the obstacle, it will accumulate. Okay, it will accumulate. It will accumulate and hitting together with the impactful of many of the particles. So you can see this particle hitting. So it become high in pressure. Okay, this is very high in pressure. The pressure is maximum because of hitting impact by many of the particle. You can see many particle accumulate and decelerate. Compared to this one, you can see. And compared to this one, how many? This is only 3 particle. This is more than 10 particle. Alright, it impact. So, Bernoulli equation state that the sum of the flow kinetic and potential energy is constant. Kinetic and potential energy can be converted to flow energy and vice versa. Cause the pressure to change. Alright. So, our Bernoulli equation, which is P plus rho V squared over 2 plus rho GZ is initially is constant, right? Okay. Sorry. Okay, this is rho, this is V, this is T. Okay. This is the Bernoulli equation, the one we derived before. So multiply this one, multiply with the rho, you will get pressure. You will get rho V squared over 2 plus rho GZ equal to constant. So in here, we can see in different way. Previously, it is flow energy. Now, it is in terms of pressure. Because this one reflect to the static pressure. And this one refer to the dynamic pressure. You know dynamic and static. Static is not moving. Dynamic is moving. That is why I got velocity. And alright. So I want to introduce you what is the difference between static and dynamic. Alright. Alright. So statics basically means static. Static pressure. Okay. The pressure if you moving pressure. Okay, sorry. You feel when you moving along, okay, moving along with flow. For the dynamic, it is a represent the pressure rise when fluid is brought to a stop. Okay, to ease your understanding, okay, we have the, for example, this is mountain. Okay, and then this is you. You are on top of mountain. And then at the mountain, you are exposed to the atmospheric pressure. The atmospheric pressure is P atm equal to 101.325 kilopascal. This is very high value, 101.325 kilopascal. This pressure is actually, okay, indirectly you cannot feel, but it is basically exert the pressure on you. on your surface. It is not only you, it exerts on the everything else. This is PATM. Okay, that is why we call as a static pressure. Static pressure is the pressure that is already there, that exert on you. Okay, you can feel. However, for the dynamic, if you have the flow from here, you have the wind. Okay, very high speed wind, and then once reaching you, it will stop. You will feel the pressure from the wind. So that is what we call a dynamic pressure. Okay, the dynamic pressure is a pressure increase when fluid is brought to stop. That means the fluid, the flow here stop at you. You feel the pressure. So when you have the pressure, let's say this is a 0.1, this is pressure, and this is P naught. P naught is a stagnation point, yeah. We call as P naught and V naught. V naught is a stagnation point also, and this is velocity. And the Z naught. Okay, we can apply the Bernoulli. Okay, apply Bernoulli. P plus rho V squared over 2 plus rho GZ plus P. Okay, P naught plus rho V naught squared over 2 plus rho G Z naught. Okay, what we can do, we can cancel out this one and this one, the same elevation. The velocity, we can cancel out. Okay, because it is 0. We can rearrange this one in order to get the pressure. Pressure naught is the maximum, right? So, P plus rho V squared over 2. Okay, this is how to get the pressure at the stagnation point. In order to get the velocity, okay, velocity of the flow here, just rearrange the equation, you will get 2 P naught minus P over rho. Okay, now you have two equations when involved with the stagnation point. Alright. So, can imagine three different pressure by holding up your hand in a steady wind. Okay, for example, this is the static. Okay, static pressure would be atmospheric pressure. Alright, and then a larger pressure felt at center, for example, center of your hand would be stagnation pressure. Okay, because why? Because at the mountain there, okay, this is you. You try to raise the hand and then this is your hand. Okay, and then the wind speed will move here. And then it will stop at your center of your hand. Okay, at your palm. You will feel the large pressure. So that is the stagnation pressure. Alright, the build up pressure will be the dynamic pressure. Okay, that means it build up, increase and increase. we call as a dynamic. Okay, finally, before we end our class, we do one example and then we close the session. Okay, a pitot tube is inserted in the air in an air flow to measure the flow speed. The tube is inserted so that it points upward into the flow and the pressure sensed by the tube is the stagnation pressure. The static pressure is measured at the same location in the flow. Using a pressure tab, if the pressure different 30 mm of mercury, determine the flow speed. So now I draw to you the diagram. This is flow diagram. Okay, this is the flow diagram and then we have, okay. You have the tube. Okay, this is what we call a pitot tube, yeah. Okay, because the area here is very, very small. Okay. This is a pitot tube. This one is a pitot tube. Alright, we have the flow from left to right with velocity that we need to discover here. Let's say it is, okay, this is B. And then we have the mercury. Right, we have the mercury at the level here to level here. Okay, so the difference here is 30 mm, right? Very small ke? Right. The difference is 30 mm. So let's set the pressure here. This is pressure. Okay, pressure. And then let's say this is the point at here. The point reaching here. Okay. This is pressure not because this is at the stagnation point. You can see the area is very small. If the flow want to enter this tube, it has to decelerate and stop and enter the pressure. Enter the region here. So this flow will enter this region. So P naught basically, P naught here is basically equal to P naught at here. The same thing. Alright. So do you think the P naught is maximum? Yes, P naught is maximum because the velocity is 0. The velocity now, velocity naught is 0. When the velocity is 0, the pressure will increase drastically. So because of the high pressure, it pushed down the mercury and then you can see the difference in 30 mm. Alright. And then we have the air, gamma of air 11.8 Newton per meter cube. So again, in order to get the velocity here, we can use the equation. Okay, we can use the equation of what? We can use the equation V equal to 2P naught minus P over with rho of air. This is the formula. Okay. So, how to get the P naught minus P? Okay. This is pressure also. We have the pressure. This pressure is equal to this pressure. Okay. And this pressure is equal to P naught. I believe you still remember. You can see this is like a manometer. Okay, this is manometer. We can use the manometer measurement technique. So previously we derived the hydrostatic equation. So we can use the hydrostatic equation by specifying the flow. I want to calculate from here to here. Alright. And then I set the reference line. This is my reference line. Reference line. Okay. So apply to the hydrostatic equation, which is P2 minus P1 equal to negative rho G Z2 minus Z1. Okay, this is equal to here, yeah. This pressure P naught is here as well, P naught. So I want to go from P to P naught. So P naught minus P equal to negative rho of mercury. Rho of mercury is given by 13550 kilogram per meter cubic. So rho of mercury, gravity, Z, which is Z? This is Z minus, okay, where is Z2? Z2 is what? Class. Z2 is not lah, minus Z. Okay, so P naught minus P is basically same here. We can replace later on. So just replace, negative density is 13550 multiply with gravity multiply with Z naught. What is the value of Z naught, class? The Z naught.
0.
0. Why 0?
Reference line.
Yes. At the reference line, 0 minus Z. Z is, what is the value of Z?
30.
30 mm. So convert into meter, 0.03. Okay. You will have the final value is 3987.77 Pascal. Okay, this one you can substitute in this equation. So velocity equal to 2 multiply with 3987.77 over with density. So this density of air, this is the gamma. So in order to get density, gamma divide with gravity. Okay, so gamma is given 11.8 divide with 9.81. You will get the final 81.4 meter per second. So that is the final value to get the velocity. Okay, is there any question? Okay, class. After this, I'm going to post in the forum what have you learned on the Bernoulli equation. Okay. Please list out at least three main idea what have you learned on the Bernoulli equation. Okay. Please let me know.
Doktor, for gamma kita kena bagi dengan gravity ke?
Betul. Yes, we need to divide. Tahu tak why we need to divide? Siapa yang tanya tu?
Sebab ke bawah.
Sebab the equation of velocity only need the density. So gamma is equal to rho G. In order to get density, gamma divide with gravity.
Alright, thank you doktor.
Okay, welcome. Okay, after this, I'm going to post the forum. What have you learned on Bernoulli equation? Please give at least 3 idea. What have you learned? Maybe you learned about the Bernoulli only apply to the incompressible, negligible of the friction out of the boundary layer. Please, I want to look at your understanding. Okay, if you have any other creative idea, please post. I want to see your feedback. What have you learned on the Bernoulli equation? Because this is going to help you in the test later on. Okay, so I give you this homework before tonight. Okay, 12 p.m. Please post your thought. What have your feedback? What have you learned on the Bernoulli equation? Yeah. Okay, I think that's all for today. Any question before we finally end the session? Okay, I think no, yeah. Okay, I end my session. Assalamualaikum warahmatullahi wabarakatuh.
Salam. Thank you, Dr.
Waalaikumsalam.